我们上次 we were we were doing cofactor expansion last time, and we did a exercise on 3x3 matrices, and then we can do a 4x4 and see how we do that. So basically, if we have a 4x4 matrix and we want to calculate the determinant of it, 0, -1, 1, -1.
Do you treat it like a 3x3? Like you cross out a row and a column and you do a 3x3?
Yeah.
Oh, really?
Mm-hmm. And we cross again to do like a 2x2. Yep.
So every matrix you can do by reducing it to the 2x2?
Yes.
Which is okay.
That's a way to calculate the a matrix with higher dimensions.
Oh, so it just becomes like the higher you get, the worse.
Right.
Okay.
Right. So we usually to do this we usually pick a row or a column that has most zeros, so that when we multiply by the factor we will just get a 0. So for example, in this case we will choose this second column. So choose second column with more zeros. Alright, so the first one we have a factor 3 multiplied by -1, and that's 1, 2. So raised to the power of 1 plus 2.
And do you not have to do a column, a row as well? Don't you cross out a row and a column?
Yeah, we're doing the first one for now.
Oh.
Yeah. So we're doing like along this column we're doing each row. Right. So the first column is 1, 2, and then multiply by the determinant of the left 3x3 matrix. That's 2, -1, 1, -1, 5, 0, 4, 3, 4. Okay, now we plus. So the second one, if we cross this line, we will have a 0 multiplied by something. So we could just leave this as a 0. And then the third row, we have 6 multiplied by -1 raised to, that's 3, 2. So 2 plus 2, great. And then we're left with 1, 1, 2, 2, -1, 1. 4, 3, 4. And then we have the last row. Oops. The last row is also multiplying 0. Yeah.
Oh, yeah.
Okay. Now,
so this is column expansion?
Yes.
Okay. So that's negative 3 times.
Locally, a singular point.
20.
The neighborhood of a singular point is isometry to
minus 1.
So this one we do another cofactor expansion, or we can do that 3 by 3 one. But if we do a cofactor expansion, we can do this
Because
along.
it's AD minus BC, right?
Yes. You can do this along, for example, this column. So first we got okay, so 1 multiplied by negative 1 raised to 2, 1.
Did you get?
You finished
Because I just did the thing.
the 3 by 3?
Because I saw it was. I don't know if I did it right though. AD minus BC and then plus minus plus.
Yes. Wait for me.
I don't
Yeah,
know.
you can keep doing the second one. Um, mhm. Mm, 4 minus 3. Eight minus 4. Mm,
No, I think definitely that.
In that case, it's likely late. That is not. The guy he drives right now. The fact that it's the very fact that he decides that guy should be used by
Okay, for the second one, okay, I got the same thing as you for -6. I got something different for -3. But I also crossed out a different row from you. I did the first.
Okay, let me take a look.
We got this as the same.
Great.
Oops. I did this row.
Mm. 20, okay. That's -4. 0 multiplied by 4.
This one is this and this.
Yeah.
So it should be 1, 2, so 3, so it's -1.
That's -4 subtract 0.
Oh, gotcha. It's my bad.
No problem. I make that mistake every time.
The exact same, but it also belongs to a word.
Okay.
Great. Okay, so this is the case of how to calculate the determinant of a 4x4 matrix. And so we've said that this method can actually help us to find the inverse of a matrix. So let's introduce the theorem. So let's say A is a invertible matrix. Right. Now, and let's define C, the cofactor matrix.
I guess what would the cofactor matrix look like for something like that? Because the cofactor matrix, is it just n minus 1 times n minus 1?
It's actually, so we know how to find the cofactor.
For each element.
Yes. For example, cofactor at 3, 2 is this. So cofactor matrix is basically you find the cofactor at every place, and then they will form a matrix.
Oh, okay.
Yeah. So after you have these two, we say the inverse of A is the 1 over determinant of A multiplied by C transpose. Okay, so let's do an example. 42 by 2 matrix, if A is 1, 3, 2, 8. Okay, and we can calculate the determinant of A equals 2, because that's 8 minus 6.
Yeah.
Alright, so since the determinant is not 0, we know that A is invertible. Alright, now let's find the cofactor matrix. So at C11, it'll
Do
be
you have a negative determinant? Yeah.
yes.
Yes, definitely.
So C11 is negative 1 raised to the second power multiplied by so in this case, if we're crossing out two like a row and a column, we're only left with this 8. So this is actually a special case of a diagonal matrix. So it is a 1 by 1 matrix, and the only entry is on the diagonal. So the determinant is 8.
Oh, so 1 by 1s are diagonal matrices. I guess
Yeah.
they're like arrows. Okay.
Okay, so then we calculate C2, C12. That's negative 1 multiplied by 2 equals negative 2. So C21 is negative 1 multiplied by 3. Good. And C22 is
1.
great. Alright, now we can write this cofactor matrix. A equals 8, negative 3, negative 2, 1. No, I mean the transpose equals that.
C transpose is
Great. So the inverse of A would equal to the determinant inverse multiplied by the C transpose, and that equals 4, negative 3 over 2, negative 1, negative half.
it just
yes, right. Okay, so this is how to calculate the A inverse. And we can actually conclude that so in the 2 by 2 case, A inverse actually equals, we know the determinant is AD minus BC if A is ABCD. Multiply by, so D and A flipped because at 1 case the determinant is D, and at D place the determinant is A. And the BC is also flipped, but also with a negative number.
I see.
And and then after the transpose, B and C are in the place. Yeah. Okay. Right. Now we can go to chapter 4 on eigenvalues and eigenvectors. Okay, so basically when we talk about a transformation from a vector space V to a vector space V, then the easiest transformations, of course, is the identity transformation. So we could have a transformation that maps any vector to itself. And a little harder for that, we can have transformations that maps a vector to a scalar multiplied by the vector, say lambda v. Lambda is a scalar. So if you remember from our first class, scalar could be a number in R or C. Okay, so these are the easiest transformations. Or simplest. Okay, so for eigenvectors and eigenvalues, they actually define by something looks like this. So let's define for a matrix n by n. If there exists a scalar lambda and a vector v, when v is not 0, it's not a 0 vector, and it holds the property where AV equals lambda times v. Then we say lambda is an eigenvector. I mean eigenvalue. For A.
But if A is a scalar, I mean A is a matrix, and lambda is a scalar.
Yeah. And we say this V is an eigenvector. Of A for the eigenvalue W. Oh, I mean lambda.
Do you mean V does not equal 0? I think
Oh, that's not equal to 0. Good catch. So this actually means this V is not any V that can satisfy this. So we know that identity, for the identity transformation, any V can map to the identity. But so when we are talking about a matrix multiplication, so matrix multiplied by a vector equals lambda multiplied by a vector. But if we change this vector, then we might not get just a lambda multiplied by a vector. So for example, if we think about the 3 by 3 matrix 7, negative 3, negative 9, negative 2, 3, and 18, 0, negative 8. And we multiply it by 113. Let's calculate it. Okay, so I think this will equal to 7, 9, 18 plus -2, 0 plus 3 multiplied by 9, 9, negative 94. Okay, so this equals negative 2, negative 2, negative 6. Okay, so if we multiply by a vector 1, 1, 3, and we got negative 2, negative 6, so the right side actually equals to negative 2 multiplied by 1, 1, 3. So in this case, lambda equals negative 2 is a eigenvalue. Okay, so however, other vectors might not have this property.
Yeah.
So in this case, both eigenvalue and eigenvector are special for a matrix. So then the question becomes, how do we find the eigenvalue and eigenvector given a matrix? Do you want to try to like multiply by another vector and see?
Yeah, sure.
Sure.
Let's just make one up.
Sure. So let's just use 7, negative 3, negative 9, negative 2, 3, 18, 0, negative 8. Okay, what vector you want to multiply?
0, 2, negative 1.
Sure. So I have negative 4 minus equals. Okay. So in this case, this vector v and this solution does not have anything in common. You cannot write it as a scalar multiplied by something. So how to find? All right, we're going to define the spectrum of A. Okay, definition. The spectrum of a matrix A is the set of all eigenvectors. I mean eigenvalues.
Is that sigma?
Sigma, yeah. Just because the spectrum starts with the S.
Oh, okay.
Yeah. And okay. So if we have a AV A multiplied by a vector equals lambda multiplied by a vector, then we can first write each side as a matrix multiplication. So the left can be stay the same, and the right, so lambda multiplied by a vector is the same thing as lambda multiplied by a identity matrix first, and then multiplied by a vector. Okay, now we can subtract the lambda IV on both sides, and we'll get the left side AV subtract lambda IV equals 0.
Is it not divide?
Subtract. We subtract the sample size.
Oh, this entire thing. Okay.
But after that, we can factor out a v on the left. So we would get a minus lambda I equals 0. Wait, I forgot to write the v. Okay, now we are having a matrix multiplied by a vector equals 0. So we've learned this. If we have a transformation, a matrix is a linear transformation. If we have a transformation mapping v to the zero vector, then we say this v is inside the kernel of lambda a minus lambda I. Okay. So therefore, let's further define the eigenspace. So if lambda is an eigenvalue for a then the set of eigenvectors for lambda.
How do you have more than one eigenvector for? Because I thought the transformation is fixed.
Yes, but so for example, if we have
Like, do you mean like instead of 113, it's like 226? But then lambda has to change too, right? So then, like, you could also like if you had that.
right. So when we talk about the vector, the eigenvector, we might have a span of a vector because some transformation is not invertible. Wait, yes. Yeah, we'll see examples. Okay, for lambda. The set of eigenvectors for lambda, and so this is union the zeroth vector, because we said the eigenvector cannot be the zero vector. Is a subspace for Rn. And we call it the eigenspace of lambda. It's the kernel of a matrix. So eigenspace is eigenvectors and zero vector. Okay, so to find eigenvectors and eigenvalues, so let's deduce some. We know that what we had was we want a vector that matrix A multiplied by it equals some lambda multiplied by the same vector for some v does not equal to 0. And that is the same thing as if we do a subtract lambda I, as we said, multiplied by v equals 0 vector. Same thing for v does not equal to 0. Okay, then that means this equation has a non-trivial solution because v does not equal to 0.
Yeah.
Has a non-trivial. Okay, so if it has a non-trivial solution, then basically means this matrix A minus lambda I is not invertible.
Okay, so if it has a non-trivial solution, then it's linearly dependent.
Yes.
And if it's dependent, it's not invertible.
Right. Okay, now if it's not invertible, we know the determinant of a matrix A minus lambda I would be 0.
Yeah.
So let's do an example. If we have a matrix A equals 1, 2, -1, 4, then let's find eigenvalues. And eigenvectors. Okay, so in this case, we would need to write the A minus lambda I. So that would be equal to 1, 2, -1, 4. Subtract lambda multiplied by I is just lambda and lambda on the diagonal. Because I is 1, 0, 0, 1, so lambda multiplied by it is just lambda and lambda.
This is A times A minus. Oh, okay.
And that equals 1 minus lambda, 4 minus lambda, and these two entries stay the same. Okay, now the determinant of it, determinant of A minus lambda I, we can actually write it. So it'll be 1 minus lambda multiplied by 4 minus lambda plus 2. Great.
Oh my god. And then you just multiply it out?
Yes. Yes, so then if we want to calculate it to be 0, so we want the determinant to be 0, so then we will have lambda equals 2, or 3.
What if it's not factorable?
Then we just use the formula,
Oh, the quadratic.
right?
Oh, okay.
Okay, now we have the lambdas. These are our eigenvalues. So then we would want to find the eigenvector. So in the first case, lambda equals 2. Okay, so we know that V would be inside of the kernel of A minus lambda I. So then in this case, it'll be the kernel of V,
Minus 1, 2.
right? So kernel of A minus 2I would be equal to so 1 minus 2, 4 minus 2, and L stay the same. Equals next one, 2, 2. Alright. Kernel of.
And then now do you do this equals 0?
Yes.
And then you find okay.
Right. So to find kernel, we set it equal to 0. Perfect. Become 1, negative 2, 0, 0. Alright, so this thing tells us we have two x's. The first one, x1 equals 2x2, x2 equals x2. And then we carry out x1. So the solution vector equals x2 multiplied by 2, 1.
Minus 2. Minus 2.
No, x1 equals x2.
Oh,
2x2. Yeah. Okay. So then in this case, we say the eigenspace for the eigenvalue 2 is the span of two, 1. So that means 2, 1 is a vector, is a eigenvector, and also like 4, 2, negative 2, negative 1, all that.
Vectors.
Right. Right. But even this case, it has multiple eigenvectors, just like this.
Wait, this case?
Yeah.
In this case.
Both cases are the same, because this case, like if you multiply by for example 226 here, it'll be very similar, because we can just take it to outside and this will just become 113, and then our result will still be negative 2 times 226.
Yeah.
Right.
But not for this example.
That one is also the same. So this one is
Like instead of 2, 1, you can make it 4, 2.
yeah.
Okay.
So that's for lambda equals 2. And we also need to calculate for lambda equals 3. But I'll just, so basically we would be finding the kernel of, so subtract 3 on the diagonals, it will leave us with -2 and 1. So then we would end up with the solution x2 multiplied by 1, 1. So then in this case, the eigenspace for lambda equals 3 would equal to the span of 1, 1. Okay. So let's write the proposition. When we were finding the eigenvalues, we were finding, so lambda is an eigenvalue of A if and only if lambda is a root of the characteristic polynomial. Okay, and in this case, our characteristic polynomial is here. Basically it was here. Yeah. Or the lambda minus 5 lambda plus 6. So this is the basically we did a 2 by 2 case and we end up with a polynomial of degree of 2.
Yep.
So meaning that the highest degree on lambda is 2. So then we say if n is a is n by n, then the degree of the degree of characteristic polynomial is also has a degree of n. Then and that means there are n eigenvalues.
You can never have. Can't you have like lambda minus 2 squared times lambda minus 5?
We can. So these n eigenvalues could be, some of them could be the same. But
does that do anything to the? Does that do anything to the associated eigenvectors?
No. That could be same. And also it could be complex numbers. Okay, so example of a complex. So if I have this matrix A equals 0, negative 1, 1, 0. Then the determinant of lambda A minus lambda I would be calculated like negative lambda, negative 1, 1, negative lambda. So in this case, I would need to solve lambda squared plus 1 equals 0. And we will end up with lambda squared equals 1, equals negative 1, so lambda equals I, or lambda equals negative I. So similar, when lambda equals I, we will need to find the kernel of negative I, negative 1, 1, negative I. And so if the second row just do like row 2 minus I times row 1, then I would end up with negative I subtract 1, 0, 0, 0, 0. Okay. And then multiply negative I on the first row. I will get 1, negative I, 0, 0. Okay, so this case, that basically means when my eigenvalue is I have my eigenspace to be the span of I1. We have a proposition. It says similar matrices. Oops. Have the same eigenvalues.
Where did I write that?
I think it's right before introducing determinant.
Oh yeah.
Yes.
How if there exists a Riemann matrix such that. Yeah.
Right. Great. Okay. So to prove that, we need also to talk about a lemma, which is similar matrices has the same determinant.
Does lemma mean like proposition?
Yeah, kind of. Matrices have.
Suppose let's start from a single variable function. So f is a single variable function.
Okay. So.
Oh, or is it like what is the term? Premise? Like you take this to be true, or are you going to prove that this is true?
Yeah, prove this first and then use this to prove the proposition. So for this lemma, we can do a quick proof. Basically, a similar matrix means A equals B, but by some invertible matrix multiplied by B. Yeah, so I can use Q inverse B Q, or Q B Q inverse is the same thing. So if I write like this, then this would mean if I multiply by Q on the end, in the end on both sides, then it will be AQ equals QB. Okay, so if these two matrices are equal, then the determinant will be equal because matrix equal means everything is equal. Okay, so then determinant of AQ equals the determinant of QB. Right, and for determinant, we know that there was one theorem saying the determinant of AQ equals A multiplied by the determinant of Q. So similar for the right side. Right, now this determinant is just a real number. So a real number multiplied by a real number is commutative. So we can actually divide determinant of Q on both sides. Then we will end up with the determinant of A equals the determinant of B. Alright, so then after we've already proved the lemma. Now we can take a look at the proposition. So proof proposition. Same thing. Let A equals QB Q inverse. And we can consider the Q multiplied by B minus lambda I multiplied by Q inverse.
Minus B lambda I.
So we know that equals so matrix is distributive, so let's distribute the B Q inverse first. So it will be equal to B Q inverse subtract lambda I Q inverse. Okay, same thing, we distribute the Q inside. It will be QBQ inverse subtract Q lambda I Q inverse. Okay, now QBQ inverse was this A. So the first term is A. And the second term, so what we have here is a factor. So we can take or a scalar. We can take the scalar out, and we are left with this QI Q inverse. And I times Q is just Q, and Q times Q inverse is I. So basically, yes, the right side is just I. Yep. Okay, so what we just proved is this Q B minus I lambda I Q inverse equals A minus lambda I. So that means.
And is the, like, for instance, like A minus lambda I, is that, like, that's just a, like, it doesn't have a name, right? It's just like a
it doesn't have a name.
of the equation.
So then we know this is the definition of similar matrices. So basically, A minus lambda I, if we treat it as a matrix, is similar to B minus lambda I. Okay, now therefore, if these are similar, we know their determinant equal to each other. equals determinant of b minus lambda I by our lemma. So then when we use it, if we find like a matrix and it need like some more work to actually calculate it, we can find its decomposition, or we can find the similar matrix after the decomposition. So if this matrix can be written as one matrix multiplied on the left and on the right by a inverse matrix, then we can just find the eigenvalues of this middle similar matrix because we know that it will be the same.
Yeah.
Okay, and then we can introduce multiplicity. So, definition. If we know that lambda is an eigenvalue of A,
Is this like normal multiplicity? Like in normal algebra multiplicity?
yeah,
Oh, okay.
very similar. Algebraic multiplicity is the same. So A is the lambda is the eigenvalue, then we define algebraic multiplicity. It's the number of times lambda appears as a root in the polynomial. So example, so if A equals 2, 1, next 1, 4, and we calculate determinant of A lambda, A subtract lambda I is the 2 subtract lambda, 4 subtract lambda, 1 negative 1. Okay, equals lambda minus 3 square equals 0. So then in this case, we have a lambda equals 3 with a multiplicity of 2. So if we just talk about multiplicity without saying if it's algebraic or geometric, then we just think of it as the algebraic. So the other multiplicity is the geometric. We say the geometric multiplicity is the dimension of eigenspace for lambda. dimension of eigenspace for lambda.
Find out all the different if you have sometimes you have only 300 vertex, but the triangulation may be a very huge number.
Number of
Okay. So then we can look at, for example, this example. So in this case, the dimension is 1. The geometric multiplicity is 1 because we have like
This idea,
one free.
one basis
vertex is
of this subspace, like one vector in the basis in the subspace. So similar for this one. This is the one vector. So 1 is the basis.
actually we have a building
Is
function
is one basis
converts
in the space of span
convert
1 1.
and filter data.
So then we say this dimension of the space of the subspace is 1. So that means the geometric multiplicity
I think
is 1.
each Monday, this Monday, next Monday I will
Okay. And one note is that the geometric multiplicity is not usually smaller than or equal to the algebraic multiplicity.
After
So for to calculate the trace, we need a n by n matrix. Trace of n by n matrix. So basically, if we have a equals a11, a12, all the way to a1n, all the way to an1, and here to ann equals the sum of the diagonal entries. Sum of ai comma I equals 1 to n. Okay, and we have a lemma. So we know the trace of a times b equals the trace of b times a. After introducing the trace, we actually have a theorem related to the eigenvalues. So it is the trace. So say if a is n by n, and lambda 1, lambda 2, all the way to lambda n are its eigenvalues. So some of them can be complex numbers, some of them can be same ones. So that means we say repeated with multiplicity. then the trace of A equals lambda 1 plus lambda 2 plus all the way to lambda n. So the trace equals the eigenvalue, the sum of eigenvalues, and the determinant of A equals the product of all the the eigenvalues all the way to lambda n. So this is the sum of lambda I. This is the product of lambda I.